1945, the world of computing was not silent. It hummed. It glowed. And it leaked immense amounts of heat. Before the digital revolution, before the smartphone in your pocket, before the microchip in your car, we lived in the age of the vacuum tube. Imagine a machine like the Electronic Numerical Integrator and Computer, the ENIAC. It weighed 30 tons. It occupied a room the size of a small house. And inside, 18,000 vacuum tubes. Each one acting as a switch for its logic. But these tubes were essentially high-tech light bulbs. Fragile. Hungry for electricity. And catastrophically unreliable. Engineers at the time weren't just mathematicians. They were thermal technicians. Desperately trying to keep the room cool enough, so the glass wouldn't melt. Every few hours, a tube would burn out. And the entire operation would grind to a halt. Think about what that means. A team of engineers. Days of calculations. All of it stopped because a single piece of glass gave out. Humanity had hit a physical wall. We wanted to automate the world. We wanted machines that could think faster than any human. But our brain was too big, too hot, and too unreliable to survive. We needed a miracle. We needed a switch that didn't move, didn't burn, and didn't need a cooling system. It wasn't just computing that was suffering. The entire global infrastructure was hitting a limit. The telephone systems of the 1940s were a chaotic nightmare. To route a single phone call, just one conversation between two people, physical metal switches had to click into place. Mechanical relays. Hundreds of them. Thousands of them. These parts wore out. They were slow. A grain of dust could kill a connection entirely. Picture a telephone exchange. A room full of operators and machines, clicking and clacking, just to connect your voice to someone across the city. Fragile. Expensive. And impossibly limited. Bell Labs, the research arm of AT&T, understood this problem better than anyone. They knew the future of communication depended on something new. Something solid. Something that had no moving parts, no heat, and no mechanical failure. They turned their attention to a strange class of materials. Materials that scientists called semiconductors. Substances like germanium and silicon. They were neither good conductors, like copper, nor good insulators, like rubber. They existed in between. In the gray zone. And that strange middle ground was the key to controlling electricity without moving a single mechanical part. The race was on. The race to find the silent switch, the one that would replace the vacuum tube. Forever. December 23, 1947. A date that most people have never heard of. A date that changed everything. 3 men at Bell Labs, John Bardeen, Walter Brattain, and William Shockley, gathered around a small, almost ridiculous-looking device. It was held together by a plastic wedge and strips of gold foil. It looked like something a student might build in a classroom. But they activated it. And it amplified a speech signal. No vacuum. No heat. No glass. No warm-up time. Instant. Silent. Perfect. They called it the point-contact transistor. To understand the genius of this moment, you have to understand the science. By introducing tiny impurities into a semiconductor crystal, a process called doping, these scientists discovered they could control the flow of electrons through solid material. Push a small current in one direction, and you could control a much larger current somewhere else. This was not just a new component. This was a new principle. The transistor was 1,000 times smaller than a vacuum tube. It consumed almost no power. It didn't heat up. It didn't wear out, and it could switch on and off millions of times per second. From that cold December morning in New Jersey, a seed was planted. A microscopic seed. One that would eventually grow into every circuit board, every processor, every digital device ever made. The digital age did not begin with the internet. It did not begin with the personal computer. It began in a laboratory. With a piece of gold foil. And 3 men who refused to accept that the vacuum tube was the best humanity could do. As the transistor evolved through the 1950s and 1960s, it moved from the research laboratory to the factory floor. And this is where the world we know today truly began. Before the transistor reached industry, a factory was a wall of copper relays. Thousands of mechanical switches, wired together in enormous panels. If you wanted to change the production line, if you wanted a machine to do something different, you had to physically rewire the entire system. Imagine that. Engineers with blueprints and tools, manually reconnecting wires, one by one. Every change cost days. Every mistake could be catastrophic. And every relay was one more part that could fail. The transistor ended all of that. It allowed engineers to replace hardwired logic with programmable logic. And from this breakthrough came one of the most important inventions in industrial history, the programmable logic controller. The PLC. A PLC is a small, rugged computer built to survive on the factory floor. Heat, vibration, dust, it handles all of it. And inside, billions of transistors execute logic at speeds no human hand could ever match. Today, your modern factory runs on these silent brains. Every robotic arm. Every conveyor belt. Every automated welding machine. Every SCADA system, the software that monitors and controls entire industrial plants, is powered by transistors working in perfect coordination. They measure temperatures. They track pressures. They monitor positions down to fractions of a millimeter. When a modern production line achieves sub-millimeter precision, thousands of times per hour, without a single human touching the product. It is the transistor that is doing the thinking. We no longer notice them. But transistors are the silent guardians of everything we have built. They are in your pocket. In your car. In the satellites above your head. In the power grids that keep hospitals running. In the water treatment systems that keep your city alive. In the aircraft that carries you safely across the ocean. There are more transistors on Earth today than there are stars in the observable universe. Let that settle for a moment. Every one of them descended from that crude device, the plastic wedge, the gold foil, built by 3 scientists on a cold December morning in 1947. From a fragile piece of glass in 1945, to a transistor so small it is measured in nanometers, smaller than a strand of human DNA, the journey of this technology is the journey of human ambition. It is the story of engineers who refused to accept limits. Who looked at a room-sized machine that burned out every few hours, and decided there had to be a better way. And there was. The transistor taught us something that extends far beyond engineering. To change the world, you don't need to build bigger. You need to think smaller. This is the foundation of our digital civilization. This is why automation exists. This is why the modern world runs. And most people have never stopped to ask, where did it all begin? Now you know. This is the Profession Archive. Thank you for joining us in the deep dive. If this video gave you something, a new perspective, a moment of wonder, then subscribe. Because there are more stories like this one. Stories about the tools, the minds, and the moments that built the world you live in. We'll see you in the archive.